Okay, welcome to the second half of the day. And because Peter is the speaker and he doesn't need a new introduction on this podium, so welcome to the second talk.
Thank you very much, and thanks for coming again to my second talk. So this will be following on, in some sense, from Yuval's and Alet's talks this morning. And as with Alet, I think the expectations for this may have been kind of gradually increasing throughout the day, which is a little concerning. But by far the most dramatic one, which I'm interested to see how it pans out, is this tour of Lapland, which was promised, particularly since I've never even been there, but that's how it looks. So anyway, let's get started. So I'm going to mostly be talking about pseudorandom correlation generators, which Yuval introduced earlier. And for me, the main motivation is towards MPC and the preprocessing model, which of course you heard about from my tutorial the other day. But there are also some interesting connections between PCGs and the notions of homomorphic secret sharing and function secret sharing, which you heard about earlier, so I'll discuss a little bit the connection there. So before getting into some constructions, I'll give you some background on the main assumption that I'll be using, which is the learning parity with noise assumption, and why this is like a really nice assumption to use for building these types of objects. It turns out to be like an ideal match, which makes everything work out very nicely and leads to some very nice constructions. So then I'll talk about two main constructions. The first is a PCG for Oblivious Transfer, which leads to this silent OT extension protocol we have. And this one it's a very practical construction. We have an implementation, and the results are very nice. It's definitely competitive with previous techniques for OT extension. And then secondly, I'll go on to talk about some PCGs for OLE, Oblivious Linear Function Evaluation. So this is what you can use if you want to build beaver triples or multiplication triples, and you have to work a little harder to build this, and we have some constructions which are not so efficient, and then some kind of recent ongoing work where we're making it more efficient under variants of the ring learning parity with noise assumption. And the hope is that this should lead to something which is also very practical, and I'm optimistic that at least with a little more work, we should be there soon. Okay, so just some background on MPC with preprocessing. So I'll go over this quite quickly since you heard it previously. But here we have this trusted dealer setup, which is this preprocessing functionality that outputs some correlated randomness to the two parties, Alice and Bob. And then, of course, they receive their inputs and run an online phase of the MPC protocol to actually evaluate the function. And the nice thing about this is you get a very efficient online phase by leveraging the preprocessing which you get from the trusted dealer. Of course, the problem is when you want to instantiate this in practice, you actually have to generate the preprocessing data. And if you have to use some interactive protocol for this, then this can get very expensive. And actually, this tends to dominate the entire cost of the secure computation with a lot of heavy crypto and computation and communication as well. So what we'd like to do is replace this with the following blueprint for secure computation with silent preprocessing. So here we have a similar setup functionality, which again you can think of as a kind of trusted dealer, which will output this time just a pair of short correlated seeds to the two parties. And these seeds will then be used to produce the same type of preprocessing data with this silent expansion phase, where just with some local computation, you can produce the required amount of correlated randomness needed for the online phase of the MPC protocol. So clearly, when you go to run this, again, you have to replace the setup functionality with an interactive protocol, unless you have a trusted dealer. But this time, because we have very short seeds, the hope is we can also have a very small and simple protocol. This results in much smaller communication, or ideally even communication for the preprocessing phase, which is independent of the total amount of correlated randomness which the parties have to produce. And this also results in lower storage costs if you do the preprocessing in advance. The parties just need to store these small seeds. Yes, and an extra benefit is that when you just have a small protocol, getting malicious security, I mean, generally compiling a passive protocol to an actively secure protocol is quite expensive, but if there's not much interaction going on, then this cost is kind of less significant compared with the overall cost. It's a nice kind of side effect of this technique. Okay, so the main cryptographic object which we'll use to do this is this notion of a pseudorandom correlation generator, which Yuval described. So we have a key generation algorithm, which is essentially the trusted dealer who outputs two keys, which then expanded to produce the pairs of samples from the correlation. And then the security notion is, as Yuval said, a little tricky to define accurately. The notion we have explicitly is given one of the seeds, say if I have the seed K0, and then I'm additionally given the output of the correlation after expansion from the other party, then this should be indistinguishable from the same seed and then a random output from the distribution for which the correlation comes from, conditioned on what comes from my seed. So this conditional part is the kind of tricky thing you need when you take into account that one of the parties, who may be corrupt, will always see the seed as well as the output of the expansion phase. Okay, so I'm going to skip this slide because I replaced it with another one, which is this landscape of PCGs, tying in with the landscape of HSS slides, which you saw previously. So starting from the bottom here in the minicrypt level, it's a little different to HSS because in this case we always want to have some expansion from a small seed to a large amount of randomness, so we actually can't do anything information theoretically. So the best we can hope for is minicrypt, where with one-way functions, we've known for a long time, in fact, back to works by Neve and Yuval from 1999, that we can generate PCGs for linear correlations with just one-way functions. And this is also used for pseudorandom secret sharing for the honest majority setup. And most of these other constructions come from a crypto paper last year, where also from one-way functions using distributed point functions, we can generate correlations for large secret shared truth tables. And then the more interesting ones are once you start to add some more assumptions. So based on kind of standard public key type assumptions, either DDH or LWE with just kind of restricted homomorphism, say somewhat homomorphic encryption, or low degree homomorphism, and you can get PCGs for kind of low degree correlations if you combine this with a simple enough pseudorandom generator. And this is based on the generic construction which Yuval described, where you evaluate the PRG inside your kind of HSS scheme, which comes from the DDH or LWE assumption. And of course, when you use DDH, you always have this kind of 1 over poly error, which you can't get rid of without some interaction. And then right at the top, if you allow fully homomorphic encryption or kind of unbounded homomorphism, then you can get fully general correlations just by evaluating any PRG inside the homomorphic encryption scheme. And then the interesting part for today is what lies in Lapland with the LPN assumption. So this all kicked off with this paper in 2018 from CCS by Neve, Yuval, and Geoffroy, who's not here, with this construction for vector OLE, which is a kind of restricted form of OLE, which gives you a scalar times by vector multiplication. So the idea here is that you can get a kind of compression of this where the seed size is much smaller than the length of the vector. And then in this crypto paper last year, we extended this to get correlations for Oblivious Transfer and also constant degree correlations, which I'll talk about later. Okay, so let's start with this LPN assumption, diving into Lapland. So previously, Alette described some construction based on LWE. Now, these two assumptions are kind of very similar, and sometimes it's a little hard to see what the difference is. So here is one of them. So we have a matrix A defined over the rings of Z mod P for some modulus P. And then we multiply it by a secret key, which is a vector, and then add some noise, which is this error vector E, the assumption that this is indistinguishable from a uniform vector. Okay, so any guesses as to which one this is? None of them. Or both of them. Yes, and I haven't really given you enough information, but it could be either. So the only difference is how you define these S and E vectors in the two assumptions. So also another difference is the modulus P. So strictly speaking, people usually think of LWE as being with a large modulus and LPN being always binary mod 2. But in this case, I'll actually consider an arithmetic generalization of LPN where you just look at it mod P instead. So this is also sometimes called the random linear code assumption because it relates to decoding of random linear codes. And we have the secret, where you can have different distributions on the sampling of the secret vector S, but in this case, they can both just be uniform. So that's the same. So the main difference here is in the error distribution. Where in LWE, of course, every entry of E is small in small relative to P, the size of the ring you're in, whereas in LPN, the Hamming weight of the vector is small. So you have a lot of kind of zero entries in this error vector E, or maybe with some probability each entry in E is 0, and otherwise it's uniform modulo P. Okay, so this small difference in noise distribution can actually make a very big difference in what you can do from the two assumptions. So just to illustrate that, here from LPN, we know we can get all of the kind of standard mini-crypt things, one-way functions, symmetric encryption, digital signatures. And we can also get public key type things like public key encryption and OT, but then we have to rely on this stronger form with a much lower noise rate. On the other hand, with LWE, we can directly get all of cryptomania, and actually a lot more, including things like homomorphic encryption, fully homomorphic encryption, functional encryption, and of course HSS, which leads to these succinct forms of MPC or 2PC. So what we're doing today is, of course, using LPN to get a form of, I say, MPC-friendly pseudorandom generator, which actually gives us some of these same forms of HSS or succinct MPC under the restriction that it's only for kind of very low degree functions and not completely general circuits. And here, again, we need a slightly lower noise rate than what you used for just minicrypt with LPN, although it doesn't always have to be quite as small as what you need for public key encryption. But yes, that's the next slide. So what is this PRG I speak of? Well, the simplest form of the PRG is just directly from LPN. So you take a secret S and an error vector E, and then expand it to A times S plus E. So typically in a PRG, you think of the seed being uniformly random, but here you can just kind of express this secret S and error vector E by taking the E as n plus m times by log of the Hamming weight random bits, and then expand these to the sparse vector E. So then the expansion of this is going from a n plus m log t. So that should be t log m. Yeah, so it's n plus t log m and getting us m bits. Otherwise, we have a very bad expansion. Okay, so now there's another construction I'll consider, which is the kind of dual version of the original one, where we no longer have a secret vector S, we just have the sparse vector E. And here we multiply E this time by a large compressing random matrix instead of the expanding one, and we get a slightly smaller output. So instead of m, we now have m minus n bits of output. The difference here is the seed size is now, again, t log m bits, but without this extra additive n bits term coming from the secret S. So if you look at the expansion of these two things, then the dual construction here, we can actually get an arbitrary polynomial stretch of the PRG, since we don't have to worry about this dimension n coming from the size of S. Whereas if you look at the security of LPN and the kind of best known attacks, then this primal construction actually limits you to less than n squared bits of output. So even if you increase m, you always have to increase n correspondingly. But in the dual construction, increasing n with m doesn't matter, at least as far as the seed side is concerned. And the best known attacks on these things are essentially exponential in the Hamming weight of this noise vector E. So if you think of this Hamming weight t, then you can imagine this being maybe 100 or 128 noisy coordinates, even when this dimension is very, very large, like in the millions or so. Okay, so how do we exploit the fact that we have this sparse noise in LPN and this kind of simple arbitrary stretch PRG to build a PCG? So this is a kind of high-level blueprint of what we do in the two constructions, which is quite simple. So basically we need a mechanism of compressing secret shares of a sparse vector, which will be this error vector in LPN, and we'll use this using FSS. So simple distributive point function type things based on one-way functions. And then the parties will expand these seeds to get the error vectors, to get secret shares of the error vector. And then secondly, they'll apply the LPN assumption by just locally multiplying with this matrix H to get some pseudorandom secret shares. Now on its own, this is kind of just like a simple random expansion of uniform bits, so it's not really useful. But if you tweak this a little bit, then you get the constructions which I'll be coming to now. Okay, so first off is the PCG for Oblivious Transfer. So this is OT, the 1 out of 2 OT. We have a receiver and a sender who has 2 strings and transfers one of them to the receiver. This is very useful for all kinds of MPC, but of course OT is naturally a kind of public key primitive and requires expensive public key operations to implement. So a nice way to work around this is the OT extension technique. So going back to this work of Yuval and friends from 2003, who showed that if you start with just a small number of seed OTs, say maybe 128 original OTs built with public key encryption, then you can extend these only using symmetric crypto and some additional interaction to produce an essentially unbounded number of OTs. So this is a really nice technique which dramatically changes the efficiency of OT and the MPC landscape. But the problem is, each time you want to generate one of these OTs, you always have to interact and send an essentially extra security parameter bits of communication for a single OT. And that's even if you want to do an OT on bits where the sender's 2 strings, x0 and x1, are just 1 bit each. So with this silent OT extension based on a PCG, the idea is that we can avoid this and generate a large number of random OTs with sublinear and AND communication. Okay, so going towards this, here is a quick kind of blueprint of the basic techniques from the IKMP OT extension protocol. So the main tool there is a way of generating correlated OT, which is a special type of OT where the sender's 2 strings are of the form W and WI plus Y, where Y is some fixed random string. And these are random otherwise. And the receiver gets one of these, VI, which can be written as WI plus the choice bit B multiplied by Y. So it turns out that using just a hash function, you can completely locally transform this into an OT on random strings. And then using a standard de-randomization trick with a small amount of interaction, the parties can just convert random OTs into standard OTs to be used on their actual inputs. So the main focus is how to build this actual correlated OT functionality. And this is what IKMP does, but at the cost of some interaction. Because the rest of this is local, so if you can do this kind of silently, then you can do the random OTs silently, which is the important one. Okay, and just writing this correlation another way, if we consider a very long vector of lots of OTs, so B is the vector of the receiver's choice bits, and then these are the receiver's outputs, then W is the vector of W's, and then each OT is of the form W plus Y. So you can look at these vectors V and W as a secret sharing. If you XOR them together, you get the vector of choice bits, each multiplied by this secret string Y held by the receiver. So by looking at this in the kind of additive, kind of multiplicative notation with y times b on the right, we see a kind of fairly natural way to build a PCG for this. Okay, so here's the overview of the construction. This trusted setup phase to generate the keys produces some seeds, which can be seen as a kind of FSS scheme used to generate compressed sharings of a sparse vector E. But this time, it's not just a sparse vector, it's actually the vector E multiplied by some fixed, say, field element Y, which is known by the sender. So here I'm writing it as an element of the binary extension fields, f2 to the lambda. So you can think of that as a 128-bit vector. Yes, so it has to be at least security parameter bits. It's not just 1 bit. That's what you mean? Yes, and y is just a scalar. Yeah. So this multiplication is just taking y and multiplying it by every bit of the sparse vector E. So this then gets us shares of y times by the sparse E, which you can then randomize using the LPN assumption by locally multiplying by the matrix H, so that you end up with shares of the random vector E. So the receiver has the random vector E, which then becomes this vector of choice bits used in the correlated OT. So this is additive secret sharing of these products, which is exactly what we had in the previous slide. Okay, so let's get into a little more detail. So the main tool I'll be using here is actually not an FSS scheme directly. It's a puncturable pseudorandom function, which we use to build a kind of relaxed version of FSS to generate these sparse secret shares. So a punctural PRF is like a regular PRF with a key generation algorithm that allows kind of standard evaluation of F. And then additionally, you have this punctured key generation algorithm, which produces a punctured key which can evaluate the PRF everywhere except for the single punctured point alpha. And of course, the security is that even given the punctured key, the remaining point fk evaluated alpha remains pseudo-random if you just have the punctured key. And there's kind of a classic ways of building this using the GGM PRF construction based on a binary tree. It gives us simple, efficient punctured PRFs where the master key has just size lambda bits and a punctured key has lambda times by log n bits, where n is the domain size of the PRF. Okay, so given a punctured PRF, we're going to have this setup algorithm generate a master key and a punctured key punctured at a random point alpha. And it will give to the sender the master key, and the receiver gets the punctured key and also the point where it's punctured. So now both of the parties can just evaluate at all of the points 1 up to n. Where the sender can compute all of these evaluations, where the receiver is missing this pointer alpha. So let's say they just define that one to be 0, and then XOR these together. Then you get secret shares of this unit vector, or weight 1 vector, which can be seen as this product of the PRF value at point alpha, which the sender knows, multiplied with this weight 1 unit vector. So this is like a note that, so this blue value is only known to the sender, whereas the sparse vector is just defined by the point alpha, so this is known to the receiver. Okay, and we also need a slight tweak to this, where instead of having this blue value be random, defined by the PRF evaluation, we actually want to kind of program this to be multiplied with a specific value y. So that's quite easy by just having the setup algorithm give out this mask of y with the PRF fk of alpha, and then use this to define the kind of missing value there instead of 0. Okay, so you end up with y times the sparse vector just from this punctured PRF setup. So note that this gives us very nice compression of the sparse vector, where the size of each of the party's seeds, given by the setup algorithm, is just security parameter times by log n bits, instead of kind of naively having n bits if they were to secret share the entire vector. Okay, so once we have a method of sharing weight 1 vectors, we can extend this naively to weight t vectors. Just by repeating this t times, so creating t independent puncturable PRF keys, then XORing the outputs of these all together. So this has this kind of factor t blow up in both the seed size and also the computational cost, which is not so nice. You can reduce the computational cost of this to actually linear with methods based on batch codes, although the seed size you still have to pay the factor t overhead. As a second approach you can do is to have a more structured error vector. So suppose that it's divided into kind of regular chunks, where within each chunk we know that there's exactly one noise coordinate. And then instead of XORing, we can simply concatenate these all together, and we require punctual PRFs of domain size n over t instead of n, and this gives us a kind of very simple linear time evaluation, so I'll compute all of the evaluations of these secret shares. One slight issue with this is that now we have this extra structure in the error pattern, which translates into a possibly slightly stronger version of the LPN assumption, though in practice we don't really know how to exploit it, and it seems to be still fine. Okay, so putting this back into the blueprint we had earlier, so we can use this to generate shares based on the seeds, which are additive shares of this now weight t sparse vector multiplied by the y, which is held by the sender, and then turn this to uniform just by multiplying with the linear value h, and because it's sort of linear secret sharing, this now gives us additive secret shares of the same y multiplied by this uniform vector, which is known by the receiver, which gives us a pseudo-random vector of choice bits for the random correlated OTs. Okay? And then you apply the standard kind of IKMP technique to hash these, and you can get random OTs, and that's it. Okay, but one thing I've missed is how do you actually generate these seeds? So of course we don't want to rely on a trusted setup or trusted dealer to generate them, so we need a way of setting up puncturable PRF keys with a ideally simple 2PC protocol. Thankfully, there's this nice paper by Derner and Shalat from 2017 where they do this to actually the kind of more complex task of setting up function secret sharing keys for a distributed point function, and we can apply the same thing when using a puncturable PRF. Okay, so the way this works is, so suppose we have a punctual PRF where, hang on, am I missing a slide? Okay, so maybe. Okay, so if you're familiar with the GDM construction, the punctual PRF, then the master key, which is given to the sender on the right, is expanded into a complete binary tree where the leaves of this binary tree, there are n leaves to find each of the outputs of the PRF. And then to puncture it at the point alpha and give a punctured key to the receiver, at each level of this tree, you need to give exactly one of the nodes to the receiver so they can compute kind of half of the nodes that are below this, which eventually allows you to compute all of these nodes except for the one at alpha. Okay. Now the method for doing this is a kind of recursive strategy. So suppose that the receiver has these special nodes on the tree for the first, say, 2 levels of the tree, and we want to compute the missing one on the 3rd level. Okay. So if the receiver has these 2, then it can compute all of the values underneath this by expanding the PRGs, which are kind of implicit inside the tree, and it's missing these 2. So we want to give the receiver this yellow node on the right so that it can compute the one here and not the one on the path down to alpha. Okay, so that's exactly an OT which we can use to transfer that to the receiver, where the receiver has the choice bit which defines which path it wants because it knows alpha, and the sender just puts in these 2 values. The problem is the sender doesn't actually know which of these pairs on the base of the tree to use and put into the OTs. The nice trick to work around this is the sender can just compute a sum of every left child of these leaves on the base of the tree and use that of one of the OT messages. Then for the second OT message, it will compute the same sum, but on the right-hand child of each of the pairs of leaves on the bottom of the tree. And then, because the receiver knows all of these ones here, except for these two here, then it can subtract these from whatever it receives from the sender and use to cancel out all of the ones except the missing value here and get exactly the one it needs. So with just a single OT, you can kind of get the next value for the next level of the tree. So that means for each of the log n levels of the tree, you just need to do one OT, and then you get the entire punctured key known to the receiver. And the really nice thing about this method for a puncturable PRF is that you can actually parallelize all of these OTs and do every level at the same time. This is because the receiver knows the path for the point alpha, so it can submit its choice bits at the same time, and then the sender knows all of the values on the tree, so it can compute its messages and just input those and then recursively compute the outputs afterwards. So this gives you a very nice setup protocol for the entire silent OT construction, where you just need to do these OTs for the punctured PRF setups. And if you have a 2-round OT protocol, this gives you a 2-round setup. And you have to do essentially security parameter times by log of n base OTs, where n is the number of OTs you want to produce in the end. And then, once you've done the setup protocol, you have to do this silent expansion phase, where here the computation is a little higher. So we have to do around n log n PRF evaluations, or PRG evaluations, I guess, to do this complete evaluation of the puncturable PRFs. Then you additionally have to do this multiplication with this parity check matrix H, or this kind of matrix for the LPN assumption, which actually turns out to be the bottleneck, because this is, if you recall, this is like almost an n by n matrix. So if you do this naively, then you end up with a very high quadratic cost. Okay, so with this 2-round setup protocol, this actually implies that if you look at the overall cost for doing OT on chosen inputs, you can also get a 2-round OT extension protocol. This is because you can actually parallelize the setup protocol with the de-randomization process, where you convert random OTs into chosen OTs. So this implies an efficient and practical, when you instantiate things in the right way, 2-round OT extension protocol from the LPN assumption, which is particularly interesting because the kind of classic IKMP protocol is inherently 3 rounds. In fact, there was a paper from Crypto 2018 which showed that if you just rely on black box access to, say, one-way functions or hash functions, then it's impossible to do better than 3 rounds. But by using the LPN assumption and this kind of specific LPN-based PRG instead of just any one-way function or PRG, we can bypass this impossibility and get 2 rounds OT extension. Okay, so on top of that, so this is mainly in the follow-up paper we have from CCS last year. We can extend this to produce active security. So as I was saying earlier, since the setup phase is relatively small, it's not too difficult to obtain active security, and there's not much you have to kind of protect against. So we present a few fairly efficient consistency checks to protect against a malicious sender. One kind of side effect is that there are some selective failure attacks which result in a little bit of leakage on the LPN error vector. But on average, this is just like 1 bit of leakage about the error vector. And so if we just assume the problem is still hard given this 1 bit, which in practice seems basically impossible to exploit, doesn't help the attacks, then everything should be fine. So we also implemented this, where the main challenge, of course, was doing this matrix vector multiplication efficiently. So instead of just doing a random matrix, as you might do for the typical LPN assumption, we rely on some extra structure in the matrix, which we do using quasi-cyclic codes. So this means matrix multiplication essentially corresponds to binary polynomial multiplication, modulo x to the n minus 1, and you can do these very efficiently using FFT techniques. So you end up with something with a quasi-linear cost around n log n instead of n squared. And there are also very fast libraries you can use for doing this, which gets us pretty decent concrete efficiency. And then the security assumption is now based on this variant of a ring LPN, or quasi-cyclic syndrome decoding, which is essentially the same assumptions used by some candidate post-quantum crypto systems, including a couple that are currently in the running for the NIST standardization process. So that gives us some kind of decent confidence that quite a lot of people are looking at it, and it doesn't really seem to be any harder than standard LPN. Okay, so just look at a few implementation numbers. So we implemented this, or I guess Peter Rindle did, and compared this with the standard IKMP OT extension protocol, or a state-of-the-art optimization of this, which is in his OT library he maintains. So if you look at the basic cost over a LAN, where communication is kind of for free and computation dominates, then okay, so when I say IKMP, I actually mean IKMP with all the bells and whistles and like the latest optimizations. So yeah, it's not actually IKMP. Yeah, so in a LAN setting, this might not be the best setting where you want the silent feature because communication is kind of cheap. But here, if you look at the runtime, ours is around 9 times slower than the IKMP cost. So that's the kind of computational penalty you're paying, which is the same in any network environment, for getting this silent feature. Then as soon as you go to a setting where bandwidth is restricted, or even if you imagine you have to pay a certain amount of money for bandwidth, and because of this dramatic reduction in communication we get from the silent feature, we quickly get kind of increasing improvements ranging from 5 times to 50 times in this restricted 10 megabit setting. And if you look at the total communication for generating these 10 million random OTs, you can see the kind of dramatic scale of the reduction from just having this silent feature going from over 100 megabytes to around 100 kilobytes. Okay, so that's the silent OT one, which is the more practical of the constructions. And now I'm going to move on to constructing OLE correlations, which are particularly interesting if you want to do MPC for arithmetic circuits. So OT you can use very nicely to do binary circuits in this GMW paradigm. If you want to do arithmetic multiplications, you need something more, which is this version OLE, which computes a oblivious linear function, ax plus b, where x is from one party and a and b are from another party. And a quick note is that if you can do OLE, given 2 OLEs on random inputs, then you can directly obtain a multiplication triple and use this for speeds like protocol, at least with semi-honest security. Okay, so here, instead of using punctual PRFs, I'm going to go back to FSS. So we need this slightly stronger variant, which is again used for secret sharing sparse vectors. Or point functions. So we have a point function which takes as input, which is parameterized by 2 values alpha and beta, where alpha is kind of the secret point and beta is the value which the function obtains at the point alpha. At every other point, then the function evaluates to 0. Okay, so FSS gives us a way of distributing this function so that we can give the parties 2 short keys representing a share of the function, which can then be evaluated to produce secret shared evaluations of the function. And similarly to the punctual PRF, the way we're going to use this is to always evaluate it at every point in the domain, so from 1 up to n, so that when you XOR these resulting vectors together, you end up with a sparse vector. Yes, well, it's still semi-honest, but if you do the setup protocol with malicious security, you get malicious security. But we don't have a way of doing that efficiently at the moment. Yeah, that's true. So I guess I'm just thinking of F2, but this yeah, generalizes to any finite field. Yes, I'll come to that. Yeah. Well, so the main goal is to get a silent OLE. Yeah. So just like the silent OT, the idea is we'll be able to compress these seeds to produce many, many OLEs, where the setup is much smaller than the number of OLEs. So this is like a, yeah, like a silent triple generation process for GMW or speeds or something. Yes, yes. Well, there are some, you can extend it to multiple parties, which I'm not going to talk about actually, but at least if you just want passively secure multiplication triples, then this naturally extends to n parties by doing it in a pairwise way. Okay, so this is FSS for a single point function. And just as before, we want sparse vectors with, say, t non-zero coordinates, which then translates to FSS for a multi-point function, which is parameterized by, say, t sets of points, and again has a seed size which increases by this factor of t. Okay, so to go beyond this kind of simple scalar vector multiplication, which we used for the correlated OT, we have to do something different. So here the idea is we're going to look at the tensor product of two sparse vectors. So if we take E and also a sparse vector F, and then look at this matrix, which is the consists of every pair of products from one entry from one input from E and one input from F, this n-band matrix, which is additionally fairly sparse. So if these have sparsity t, then the matrix has around t squared non-zero coordinates. So this matrix has size, say, n squared. We can additionally secret share this using a multi-point FSS, this time with domain size n squared instead of just n. Okay, and this time we need t squared point FSS, which we can use to distribute shares of the tensor product. Okay, so then the construction will take these t squared FSS seeds and distribute them to the two parties. And then they can do the same kind of full domain evaluation, this time on all of the n squared points, and they'll each obtain this random matrix, say n by n matrix, such that when you add these together, you end up with the tensor product of the sparse vectors E and F. And now the goal is again to use LPN to randomize these. This time, if we first multiply this, say, on the left by the matrix H, then this is serving to randomize the vector E. Then we multiply on the right by H transpose, and that, by the linearity of the tensor product, that'll actually give you H times F on the right. So you have this tensor product again, but now on these uniform vectors under the LPN assumption. Okay, so what that gives you is a PCG for tensor products. So it's not just OLE, it gives you like every pair of products from two length n vectors. So the output is size n squared. So computationally, this is now very expensive to generate because we need at least n squared operations just to compute all the outputs, even if we only want n OLEs or beaver triples. But if n is big enough, then we'll end up with something with sublinear communication or sublinear seed size, which we can expand into a larger number of triples. And this can also be extended, interestingly, to higher degree correlations. So actually, for any constant d, it's kind of very natural to, instead of taking a tensor product, you take this kind of d-wise tensor product, tensoring d independent sparse vectors together. This costs you around n to the d operations. You can get arbitrary degree d correlations with a PCG. No. So it's not from a small number of beaver triples, it's from these very specific FSS seeds. Yes. Which is why I say it's not strictly OLE extension or triple extension, because you start with something that is different and much more structured. But then you locally compute many more beaver triples or OLEs. As well as producing these OLEs or beaver triples, a kind of interesting connection here is that this actually also implies a homomorphic secret sharing scheme for degree D functions, just on the LPN assumption. So to see this, so if we have the PCG with seed generation and expansion algorithms for this degree D correlation, which we can write as R, of R tensor R for some random vector R, and then we're going up to this D-wise tensoring of R with itself, D times. This is essentially just every kind of up to degree D monomial of all the components of R. And then in the HSS scheme, to share some input X, we will just take the seeds from the PCG for this correlation, distribute those to the two parties, and then publish a one-time pad encryption of X under this random vector R. So where X is here a kind of very large vector, imagining we're doing HSS for some degree D function of this vector. And then to evaluate that, if we have some degree D polynomial P we want to evaluate on X, then you can write this in a polynomial of R by looking at the public information X prime, which we have, and then this is then actually a linear function in this expanded correlated randomness R, consisting of the tensoring of the small r with itself up to D times. So having these degree D expansions of R gives us, is we can just locally compute on all of these shares and end up with a sharing of P of X. And this is really interesting because previously the only kind of known ways to get HSS beyond like very simple things like point functions or decision trees was to immediately go up to these kind of heavy cryptomania things like LWE or DDH with 1 over polynomial error. And now from us, this almost mini crypt or Laplandish assumption with LPN, we can get something which is at least somewhat close, even if it's restricted to constant degree functions. Okay, but the problem with both of these is that you've inherently got this n to the d cost, so even for degree 2 correlations, if you want to produce 1,000,000 triples, then there's going to be at least 1,000,000 squared operations, which is way, way more than you want. Okay, which brings me to the more efficient candidate construction, where instead of using LPN, we'll use a ring version of LPN. So recall that with the silent OT, I said already that we're actually using this ring version of LPN to improve the computational efficiency, but it's not strictly necessary, so you could also instantiate it with kind of any variant of LPN for which the matrix gives you something pseudo-random. Whereas here we specifically rely on a polynomial version because instead of tensor products of these two sparse vectors, we're going to be doing polynomial multiplication. This is kind of analogous to how fully homomorphic encryptions based on ring LWE work, if you're familiar with that, and the kind of Recursti-Vaikuntanathan schemes based on LWE and ring LWE. So if we have two sparse vectors E and F, and now represent these as a vector of coefficients of polynomials over ZP. Okay, then we can compute the product of these two polynomials modulo some polynomial, say x to the n plus 1. This gives us another vector of length n. But because x to the n plus 1 is very sparse, when we're reducing modulo this, we don't actually change the error weight. So here we have exactly t squared coordinates in the product. The nice thing here is we have something of length n, and we haven't expanded to n squared, and we still have a multiplication of some kind. Okay, so what we'll do to generate the PCG is take 4 sparse polynomials, so EF and then E prime F prime as well, and then distribute shares of the tensor products just of these length 2 vectors of polynomials, E prime with F prime. So now there's just 4 of these polynomial products we need to distribute using FSS. So this is 4 t squared points, which are secret shared over a domain of size n. Okay, and then the output of the PCG is going to be obtained by randomizing these polynomials using the ring LPN assumption. So what we do is take a public random polynomial h, which is going to serve as a kind of replacement for the matrix H before. And then we'll think of, so say one random output is given by H times E plus E prime on the left, and then the other one is HF plus F prime. And then given these shares of the tensoring of these polynomials, which we get from the FSS seeds, then we can compute locally a sharing of this product here, so that parties can get shares of the degree 2 function over the polynomial ring. Okay, so this gives us a PCG for kind of a single multiplication over this very large polynomial ring of degree up to n. But if you choose this ring nicely enough, such that x to the n plus 1 splits into linear factors modulo p, for example, then this is actually equivalent to getting n OLEs in ZP, which is exactly what we want to do. As compared to the previous one, we had to generate this entire tensor product. Now the polynomial product gives us just the OLEs. Okay, and then the security of this is now not based on any general LPN assumption, but instead based on this ring version of LPN, where this value H and H times by S plus E, where S and E are these small sparse polynomials, taken modulo P and modulo, say, x to the n plus 1, or could be some other polynomial f of x, is pseudorandom. And it really helps if we have the f of x splits into linear factors, which additionally gives us some more structure in the underlying ring, or it's actually the same structure that is used in FHE schemes when you want to do efficiency with these kind of SIMD techniques when using ring LWE. So just like ring LPN and LWE previously, this assumption is actually identical to ring LWE, just with a different error distribution. And as far as we can see, this doesn't appear to introduce any significant weaknesses. It hasn't been studied before, but we've been looking into kind of standard possible attacks you can do, and there are some things that this structure of f of x can maybe help you when you're attacking it, but at worst it should hopefully be counteracted by just increasing the noise rate a little bit, maybe doubling the number of noisy coordinates or something, and it seems like it should be a hard assumption. And then under this assumption, we'll get a PCG for these OLEs where the computational cost is this t squared factor for expanding and computing all of these FSS seeds, and then just something quasi-linear n instead of quadraticing n for doing the polynomial multiplications. So to sum up, we have these two PCG constructions, both based on variants of LPN, which is this kind of really nice match where the sparse vectors tie in very nicely with FSS schemes, which allow you to distribute shares of these sparse vectors and do things with them like multiplication. So we can get OT, and you can also get vector OLE based on almost the same as this correlated OT approach I showed you, which gives you very practical protocols, definitely competitive and favored over previous approaches if you care about communication in your protocol. And this nice 2-round OT extension protocol, which you couldn't get efficiently otherwise. And then we have the PCG for OLE, where if you want just feasibility or something not very efficient concretely, you can do it from standard LPN. Otherwise, we can get what should be an efficient construction based on this variant of ring LPN with a special polynomial. So this still needs a little bit of work to kind of fully analyze and optimize some efficiency, but I think that hopefully once we find this all out, it should get you something practical, just like the silent OT. But there are still lots of open problems. So for the OT case, we have this matrix H we have to do this multiplication with, where we use these codes based on a polynomial multiplication, which get you quasi-linear overhead. Now, it's possible that maybe if you instantiate with some different codes, you might be able to get something linear time, which could improve the computation by maybe up to a factor 3 or 4 compared with the previous times, which would get you much closer to the computational cost of IKMP style protocols. Yeah, I don't know. Potentially, that would be very nice. And then for the ring LPM one, the main thing which needs looking at here is the security of this ring LPN assumption. So we've been looking at that into a little bit ourselves, but hopefully once we put it out there, it will encourage more cryptanalysis to have a look and study this once we have this nice application. And then outside of OT and OLE, of course, there are other correlations that would be nice to have PCGs for. So I mentioned earlier we can do something for truth tables based on just a distributed point function. There, what would be very nice to have is to have a method of setting up the seeds with active security. So I mentioned this approach based on OT with passive security, but to get that with active security without having any kind of extra leakage on the underlying points seems very hard. And other correlations would be nice, include things like random shared bits. If you have, say, random secret sharing over ZP of a bit, that can be useful for a lot of applications at MPC. And maybe also something like garbled circuits, which is much more ambitious and complicated. It's a very non-trivial correlation, but if you can compress a garbled circuit, obviously that would have a lot of amazing applications. Okay, that's all. I'll happily take questions.
Yeah, questions? There are no more questions, so let's make it happy with the gate.
Oh, again? Thank you.